Hello, everybody. Welcome back to the second class of Polymer Physics. Last class we have had a good introduction about the polymer physics concepts, and we discussed the many aspects of chain conformation. Specifically, the class we discussed how big the polymer chain would be look like if we give in polyethylene as an example. And we also discussed how does the polymer chain will behave when it's fully compact. So I'm very glad to continue today's lecture. We're going to talk about our first chain model, about free joint chain model, as well as use the random walk as introduction techniques about for us to understand what is going on if the chain is behave like 3D random walk in space. So without further ado, let's get started in today's class. So before I start, I want to ask everybody some questions related to today's class. So as you know that conjugated, not conjugated polymer, just polymer are generally linked by those covalent bonds together. So for example, polyethylene, what we talked about in last class, those materials are carbon-carbon bond linked around its backbone. So it's very important for us to understand how does a polymer chain look like in three-dimensional space. So before I give everybody any example, I want to ask everybody to think about it and for a second and trying to guess what they would behave like. Okay, I think everybody is thinking actively and hardly about how does this polymer chain would behave in three-dimensional space. Very good. So that touches our very important basic concept about polymer chain conformation. It is very critical for us to study that because those chain conformation usually happens at nanoscale, but they would later be translated into macroscopic scale, so that we know those macroscopic scale would further determine our thin film's mechanical property or other related property. We give an example that last time, and we asked everybody about 280 kilodalton or kilogram per mole polyethylene, how big the chains are. We discussed the two very important concepts. First is the contour length, which is discussed about how big your polymer chain is fully stretched. Okay. So it still is very important aspect in today's lecture, as well as the fully compact chain. And we roughly know that a fully compact chain roughly is on the order of few nanometer, while those fully stretched chain, we're talking about on the length scale about microns. So let me give you a little bit spoiler. So free joint chain, or something we also call a Gaussian chain, is sitting somewhere in between. It's not that big, but neither not that small. So today's lecture is very important because we're gonna use what we learned today to figure it out how really big they are. When we talked about big, how big they are. When we talked about small, how small they are. So we will give you guys some numbers. All right. So to start my discussion, I want to use example to help everybody to visualize how the chain is assembly or behave in three-dimensional space. As you know that random walk is commonly used to explain how somebody is walking around a grid, for example, as shown the case on the top left. If you have a chance to go straight or back or left or right, so this will, if this is totally random, then you would have a phenomenon called random walk. And random walk is quite phenomenally important because many of the polymer physics property can be linked to this very simple model, a random walk. Okay? So let's also discuss something related but different is what about three-dimensional space? Think about nuclear diffusion or think about computer science. They all relate to random walks. As well as, interestingly, anthropology also relate to the random walk. How do you think about human beings migrate and move around along the human history? That's very important as well, as we know that some ancestors are moved around and almost in a random fashion. Okay, so that's also very important. We need to discuss that as well. Next topic is about stock market and gambling. Although you might be surprised why a polymer physicist would talk about that, but actually, this gambling behavior is also something related to random walk. So, Russian roulette is a great example. You could bet it will be a white color or black color. So by this is almost a 50-50 chance, right? But each row is not dependent on previous row, so you cannot simply assume if you have see three whites, the next will be black. There's no correlation in that. So this will be related to what we're going to discuss today. We're going to talk about a very simple case is random walk in one-dimensional space. So here is a nice, interesting plots about random walks. So we're gonna use that as an example. Use the next 5 to 10 minutes to discuss what the walk look like and how does that affect our findings. So for example, in this random walk, we're gonna first discuss how does a polymer, how think about you are as human being, not necessarily polymer, start at the starting position at 0. So now you have two options, either go forward or go backwards, right? So either way, you would advance a number of 1, either positively or negatively. So imagine now you have a coin you could throw, and depends on how you throw it, right? You could either get a head or tail. This is pretty much common in, for example, in the National Football League when they throw it to pick who's gonna start the kick. Same thing here. But now imagine you, the students, are sitting in front of the computer, can help me decide where I'm gonna move. So you throw it. If it's positive, I as a professor will move in forward, and I could move backwards if you throw the tail. So imagine, well, this is what is going to happen if you throw 1 positive, 2 positive, 1 negative. This is where I'm going to go. I'm going to go from 0 to 1, 1 to 2, then back to 1 again. If we take each step is bigger in the step size of 2 instead of 1, we could move 2 blocks at the same time. So we move to 4, and go back to 2 again. So if we run a nice, interesting, small computational simulation codes, we can get what would be the randomness look like. This will be this paragraph exactly. So what you're looking at is the step size versus step number. So we can think about, everybody gonna start from 0, so now you could take different trajectory. So this goes down, for example, purple, you get more negative values and you pretty much stabilize it there. But this yellow start off positive, then it's suddenly more chances to get to a negative value. So you can see there's going to be a distribution of where you're heading towards. And if you throw the coin, 100 times, there's many possibilities. You might not get exactly like any of those lines, but those lines represent what the potential pathway can be look like. So it's still quite useful for everybody to see and compare. All right. With that in your mind, now think about what it would be the step size effect. So the step size, when we increase it, we might ended up different positions. It's either going to be more different from where you start off this position 0. So for example, in the first case where we start from this position 0, we could either go up to 20 or minus 15 in this case. But in a very odd chance, if you have every single throw will be a positive, then you could have ended up all the way to 100. But this is very rare, almost impossible. You're throwing 100 times, each time is ahead. Okay? In terms of step size, let's look at it on the right. So what you would see is it's still going to be quite randomly distributed. Just because each step is bigger, now we have the position instead of limited, like in one case shows between 10 and 20, now you have potential and more spread of your findings. Why we want to use this example? Because when you think about polymer chain, it's basically is a random walk in three-dimensional space. It's not going to be one-dimensional space like this, but the fundamentals are pretty same. Think about each walk has a defined distance of the bond length L. L is known, for example, carbon-carbon bond is going to be 1.5 angstrom, so you know where exactly this value is. Now the question is, for a number of steps you're going to take, how this would be impacted, right? So this comes to this value, what we show here. If we take different options, let's say 50 different walks, as we're showing here, from 0 to minus or positive, these are the options, but let me draw it bigger. So now you see the final position can be as small as 0. That means you go in left and right, you ended up equal chance of getting the positive and getting the negative steps, so they cancel out each other. At the end of the day, it's equivalent to you didn't take any move at all. So you're going back to where you start from. That is position 0. Okay? And it's going to be a near Gaussian distribution, as you can see. There's where you ended up with higher and higher position will be lower chance. So you ended up with position 1 will be slightly higher chance than ended up position 20. That makes sense, right? If you take the bigger step, that would impact a more broader distribution, because that each step is bigger, so you have more possibility to reach, final step of 20. Again, this gives you is what impression that where you end value would be behave like in 1D walk. Okay? But how about end-to-end distance? This then now will be different what we showed in previous cases where you end position. End-to-end distance now has a possibility going from the frequency of 0 to frequency of 20. Okay? You need to multiply by chance of where you get, multiply by the distance value where you get, right? So we have a lot of chances that 0, but that means the distance will be 0. We have some chance of have end-to-end distance of 1. If you go back one slide, you have some chances of ending up at this value 1, right? But the distance from 1 to 0 multiplied by chance is also going to be increased slightly. Then you keep counting. You actually will get an initial increase. That's because although your probability drops like we show in the curve below, imagine that probability will peak at 0, then it will drop down. But the distance also increases over time. So distance multiplied by probability will be what you show here. And you can see there is a roughly peak. We will go into more detail in the later stage of discussion. And this will also reflect in the second case where you can find end-to-end distance. When you have a larger step, there's going to be follow similar probability, but it will show up at slightly higher end-to-end distance now. So how do we actually calculate about probability of where you ended up? So we're going to use a very simple case. Let's use an example. For example, if you are thinking about having, not thinking about, but give birth to the kids as an example. If you have 3 kids, what the chances of all of them are boys or all of them are girls, right? So this can be a great example to explain the probability. So for each birth, you would have an equal chance of having a boy or girl. So you would have 50%, 50% chance. So if you want to have 3 boys, that means you have to take 50% chance in the first one to reach the boy, and another 50% you reach the second one, and additionally 50% to have the third one. So your chances of having 3 boys would be 0.5 multiplied by 0.5, then multiplied by 0.5 3 times. that comes down to a probability of 12.5%, very low. Well, this would be explain what the probability equation we show here. That means the occurrence of the event, that means how many chances you actually get this event. How many chances of you having this event occur? Okay? So, for example, if you have a boy, that means you're gonna have only a little bit of them versus a lot of those chances. So they are totally different. So coming back, so occurrence of one event versus occurrence of all events will determine what the probability. Okay, individual pathway versus all possible pathways is another way to define it. So for example, if you think about scenario below, what the chances of getting to this position in 2 steps? You would take from A, from B, from C. If you take 2 steps to here or there, you couldn't reach it, right? So there is a total of 7 possible steps you could take. That means you could take 1, 2, 3, 4, 5, 6, 7 different ways, but chances of reaching it, as shown here, would be only 3 chances. So your probability of achieving what you want in this case is going to be as low as 3 divided by 7. That's a probability. We're going to come back to this topic one more time when we talk about the probability of distribution of the single chain. As you can imagine, for an individual chain, they may not, their conformation is changing over the time. So like me, I move around, my hands can be smaller or longer. The polymer chain, again, it's moving. It's not stationary if it's in the solution, for example. Or if it has a polymer has millions of polymer chain, not 2 of them will look like exactly the same. The chance is low. So each of them will adopt a different conformation. And this conformation should be considered. So a lot of time when we discuss the chain conformation, we will discuss averaged end-to-end distance, for example. In this chapter, we're going to talk about this. And when later on, you will also see we could either calculate out what is individual chain. So that will come back and use this probability to tell you about the chance. Now, think about the random walk. So we have discussed a 1D random walk at the beginning. You would also have 2-dimensional random walk. That means your chain will go to all directions, like showing here. These are lattice, up and down, left and right. So counting the number, you can draw out a 2D random walk case. And polymer is actually happening in 3-dimensional. It's not a 2-dimensional space for the polymer chain. So what you will see is 3-dimensional space for what the chain conformation look like. And you will get all these chain conformations from what we show here as 3-dimensional space. Okay? So in this case, you was also going to be related to something called interstep correlation. This is what means is for a truly random walk process, there will be no correlation between any of the location in the walker usually. The length of each step is basically kept constant. It satisfies our polyethylene case, for example. That means each carbon-carbon bond will represent 1 step. Okay? In a degree of permutation, you have 2 bonds, so that's corresponding in 2 bonds happening in your material. Okay? All right, let's continue to talk about another important aspect is a random walk. There's 2 ways. One is called excluded random walk. That means you cannot go back to the same spot one more time. So once you already stepped in the same place, one place, you cannot go back again. That's basically represents a real chain because the chain cannot occupy the same space. You cannot have 2 carbons sitting at exactly same location. The other case would be if they can overlap with each other, that is sort of agrees what we talked about in ideal chain model. So in the ideal chain model, your chain is no longer has to be avoiding each other. They can sit on the top of each other. And first, let's talk about this case where your chain is like ideal chain. They can sit on the top of each other. Okay? So in three-dimensional walk, we usually use a vector concept to discuss what our each work. So each step will represent a vector. So for example, in the first step, we can use from R0, where is 0 carbon, to first carbon, where is R1, as shown here. So this will be represent the first vector from R0 to R1. And please be very cautious about the difference between scalar and vector. They are very different. So the scalar is only a magnitude of the distance. For example, if I drove to somewhere, the mileage in my car, for example, from Harrisburg to nearby New Orleans is a great example, that I usually drove about 120 miles to New Orleans. So scalar means 120 miles. It doesn't tell you which direction you drove. But to get to the right destination, we need a vector. Vector means it's pointing to a direction with angle, as well it shows the distance. So for example, if I only tell you New Orleans is only 120 miles away from us, I don't tell you where direction it is, you could have drove 120 miles to other direction. For example, if you go southeast direction, you can reach to Mobile instead of New Orleans. So in the polymer physics, when we discuss a chain conformation, the vector is also important. That tells you where you start off and where you would end. So that's basically not, this would be representing a distance, okay, not just a value. So we got R1, R2, R3. If we can combine all these vectors together, we would get an end-to-end vector. So REE, let me use my pen and show you guys. This is called end-to-end, abbreviation of EE. That is end-to-end distance for REE, okay? So use that, then you would be able to get the value what you needed as end-to-end distance. So in the vector concept, that we know it's very straightforward. The vector is just a sum of a single vector. So R1 plus R2 plus R3 until it's all the way to the end, then we would get REE. So in other words, it's missing here. It's actually missing a sum symbol. So let me write REE vector will be equal to sum of I equals to 1 power n Ri. Okay? So let me also zoom in so everybody can see this part clearly. REE would be related to this value. And this is important in reasoning that if we use this simple concept, we can already use a simple mathematical terms to get what end-to-end distance is. So as we know, the average of the vector, if it's a random walk, that means vector can be pointed every single direction. And we know because of random walk, the average what we got, for example, in this slides, the average value of all the data will be ended at 0, right? So that is the reason we don't want to use just an average of REE to describe our chain conformation, because it's not useful. REE average will be 0. And by the way, this symbol represents an average symbol. So that will tell you what the average value for a certain parameter will be. Let's go down to where we have talked about here. So in terms of random walk, then we have to convert a vector to a scalar. So in the mathematic way, we have um, uh, absolute is a mathematical treatment to take a vector to a scalar. So for example, I could write, let me move up. So I could write, let me go back one more time. Let me first zoom in here. What that mean? An absolute of vector A would means the distance of this value. So absolute will convert a vector to a scalar. So let's say if I know the distance is L and also have theta component in it. For example, I have L is here, I have a theta angle going from this direction. If I take absolute of this A vector, this is going to be L, because the angle component will be taken away. Looks like when I convert this from Word document to PowerPoint to PDF, somehow the equation is messed up. Let me make sure I have the right formatting. Let's see if the PowerPoint might work. Okay, so it looks like it's loading up. Let's hopefully this is working so we can view all the equations in a right format. Let's see. All right, this is actually working much better. Okay, so I hope everybody can see it, and this is a pretty big already. I think should be pretty good. Let me try use a slideshow so that it makes even bigger. All right, nice, perfect. So we can stick with this phone instead of use the other one. So 3D random walk is what we show here. Now, all you need to do is take absolute, and what you can do is use IE square, IE square. Then you can take about later on use end-to-end distance will be equals to root square of REE square. Okay. So that means you only consider distance. There's no vector or angle components into this. This is important. So now each Rn, by definition, RE distance is basically Rn squared, right? RE end-to-end distance is from Rn. And by the way, Rn is already defined in the last chapter. We know Rn vector will be equals to I equals 1 to n and Ri vector. So that means Rn, this will be the end-to-end vector. Now, this in the next we wrote Rn. It's basically defined as in the last equation we have shown. So it's very nice, right? We have a very simple equation can describe what we already know is a 3D random walk. We know that our sample will be equals to I equals to 1 to n. Then we can use this mathematics expansion. And we know each Rn will be equal to exactly the value shown here. So each one Rn will be equals to R1 add to Rn. Then if you use the dot product to multiply Ri to another Ri, you will end up with another mathematical form. So that means it's a sum of Ri and Rj, and I would equals to from 1 to n, j would equals to from 1 to n. And if we further expand this, we would get these two terms. One called self-term. That means it's basically Ri dot Ri itself, and it will make a huge difference, as we will explain later. And you would also separate the rest out to the cross term. And regarding the difference between the self term and cross term, we will go into a little bit more detail. But the simplicity is Ri multiplied by Ri itself, or called self term, can be further simplified to Ri squared. Okay? So, why? Let's review one of the term called dot product. Okay, there is dot. If we dot Ri multiplied by Rj, this would be related to the scalar. We take absolute, we only consider length, and Rj, we only consider Rj's length, and cosine theta. So if we draw, this would be Ri, and this would be Rj. So this basically says we're gonna what dot product is equal to Ri, Rj, and the angle between two multiplied by cosine theta. Okay, so this should make you guys see it more clear. This is called dot product. I multiplied by Rj will be absolute I Rj. So that's two scalar multiplied by cosine theta. And cosine theta is basically means the projection of Rj along the I's direction. The physical meaning of that is basically saying if I have two products and I multiply one over the top of the other, that means dot product means how much directionality I have from the second vector sitting on the first one direction. If they're perfectly aligned in the same direction, that happens when means I multiplied by I, and as you can see, if we have let's row somewhere empty, so Ri dot Ri, this will be equals to Ri multiplied by Ri absolute, so it can't erase, so don't worry. It should not have additional square. Now, multiply by cosine theta. So if two are pointing in the same direction, that means theta would be defined, would be equals to 0. So cosine theta would equals to 1. In other words, this would be equals to Ri squared, absolute square. If we know the distance is L, or R distance is bond length L, we can directly row this first term will be equals to L squared. And we have total number n of them adding together, we will get NL squared term. Okay. So the second term is called cross term. This actually will cancel out with each other. When there's Ri dot Rj, for the free joint chain, what is going to happen is your chain gonna have always find a chains point to the opposite direction because of random. Free joint chain means you have equal chance to point in all directions. So your chain point to the right will cancel the chain point to the left. So what we're left is a term that is will be 0. Okay? So again, here we reviewed one more time what is dot product as shown here. So this will be what the definition of the dot product, and that will be what we define as two terms. First is the self term. This will be equals to NL squared, and this is non-self term. This is called a cross term, and this will happens to have two terms, I equals to from 1 to n, and when j is not equal to I, this is very important because j equals to I is basically means it will be self-term I dot by Ri. Adding them together, you would get all the data as shown here, and you can get what shows equation is valid going to be for any random walk chain. So we already mentioned the self-term, the theta equals to 0, so cosine theta are going to be equal to 1, so you would have ended up the angle term will go away, so this will be L squared. Or cross term will drop out because the average of cosine theta is equal to 0 for free rotating chain. And also free jointing chain, sorry, not free rotating, free joint chain. So this will leave you a very simple end result. N to the n distance square will be NL square. What that means is your end to end distance can be simply calculated out if you know the number of bonds along the backbone multiplied by bond length. And this is very important because remember this is also a square, so end to end distance REE average will take a root square of the term on the right, so it will be n power half multiplied by L. And this tells you the end-to-end distance proportional to the length L, right? The bond length doubles, your end-to-end distance will double. But more importantly, it's dependence on n. So what show here means your bond length doubles, your end-to-end distance, sorry, not bond, your number of backbone unit doubles or molecular weight doubles, your end-to-end distance is not double. And it simply take a factor power of 1 over 2. So that means your molecular weight doubles, your end distance increase by root 2, which is 1.41 of original length. If your molecular weight quadruples, that means your end-to-end distance will be root square 4 or twice of its length. Okay. So I think for today's class, we're just going to end it here. So in this class, we talked about concepts about random walks and how does random walk is related to our polymers chain conformation. And we also had some time to discuss about this end-to-end distance for a free joint chain. And pay attention to what is a self-turn and cross-turn, because those two are very important for us to explain how the chain will behave. All right? So with that, I would like to end today's class, and I'm looking forward to the live discussion this morning. See you guys later.